Hi everyone, welcome to this our second on the colloquium series. Today we have the Dr. Chu Seng-woo. He's our own proud graduate and a PhD from our program. Dr. Woo graduated 2015, actually graduated 14, right?
15.
And he 15, but he did a he started with Binghamton University next to, I think, close to New York. I by myself visit his university to see him. We had some Chinese restaurant over there, and then after that he was very productive. He did this because of his productivities. He did charge of the graduate director before joining into the University of Tennessee. Now I can see that University of Tennessee has a very strong cognitive, a lot of GIS remote sensing faculties over there. So we're very good. This year, as I told you, he's very, very productive. This year, he just published 9 for only 2020 publication. And I got very good news that he just got I asked before you guys joined about his the funding, and he applied. He said he just applied yesterday. Good news is today, part of his he had a co-PI. He got a U.S. Army Corps of Engineering, $250,000. So he got a half of those 125, so that he can have some graduate students and research. So I sent you CV. His CV is about 20. He did only 6 years as a faculty. Is very productive, and he's always challenging the new things. He's not afraid of adopting the new things. He was been in the classes TA during his PhD. He was one of my best TA, and he always actually helpful to provide this further. So, and today we're gonna learn what he has actually moving forward, take a new technology and how we're gonna expand our geography domain. Without any further ado, let's welcome Dr. Wu, and I think you're in charge. Everybody, welcome him.
Hello, everyone. Thank you, Dr. Kim, for the introduction. And it's great to be back virtually. I spent 6 years at UC, 2 years a master and 4 years PhD. And I graduated in 2015. Then I joined Binghamton University in New York for 4 years. And last year, I just moved to University of Tennessee. And so the title of my presentation is Interactive Mapping and Analysis with Google Earth Engine and Open Source GIS. You can access the slides by scanning the QR code at the lower right corner, or you can type the URL gishub.org/UC. I also put the link in the Zoom chat box. So if you're able to go to the chat box, you can click the link and to access the slides. And so right now I'm serving as the editor for Journal of Remote Sensing and Wetlands. And you can check some of my academic profiles here if you're interested in learning more. So for the past few years, I'm most of my time have been spending trying to develop some open source software packages. And so you can check my GitHub repo for some of the work that I have done during the past few years. And so for today, I'm going to primarily focus on the package called geemap. I'm going to get into that shortly, but as you can see, so some of these packages right now are quite popular in the open source community. So hundreds of people actually using this right now. So if you find it useful, you're welcome to look at my source code and contribute to this project. So here is the outline of my presentation. First, I will going to briefly introduce Google Earth Engine, and then I'm going to show you the package that I developed called geemap, and I will show you some tutorials and some of the key features that for this package. So I will also introduce the Google Earth Engine QGIS plugin. And lastly, I'm going to show you some application, what kind of things you can do using Google Earth Engine. On the right here shows you on animation. So this is the animation of Landsat time-lapse for the past few decades. So since the 1984. So basically every year you have one imagery. And if you like, you can click the link here, the web app to open this one on the browser. And so this is very easy to do. If you want to evaluate the changes of the landscape using Landsat data archive, you can try out the app, and all you need to do, you can, for example, you can use the icon on the left, upper left corner. You can source any location. For example, I can say LC. And once you get to the location on the left side here, you can draw a rectangle. For example, I want to look at this region, and then you draw the rectangle here. And for here, you can change the title. You can select different bank combination. You can also change the speed. So basically, we're trying to create an animation showing you the changes. And you can customize the year, also the month. You can change the color and also the progress bar. So after that, just click create time lapse. And so basically, this is the app I developed using the package. Then you go to the Google Earth Engine data archive, basically do all the processing, and then mosaic all the imagery together, and then create an animation. So this is a quick way that if you want to see the changes. I think I have some in here. So this is what the outcome looks like. And you can turn the layers on and off. So it doesn't have to be this location. It can be any location. You can change different bank combination. And after that, you can download this one to your local computer. So you only need to just click the link, and you will download this animation so that you can put it on social media or on the website or anywhere you want to demonstrate. So very easy to do. And you don't need to, as you can see here, you don't need to write any line of code, and then you can create animation like this very easily. I also provide the source code. So if you're interested in learning more like behind the scene, what this one is actually doing, you can click the link notebook, and you will take you to my GitHub repo. And from there, you will be able to see like the source code behind this app. I also have video tutorial how to show you how to do that. I'm going to show you later. But this is just give you some like preview, like what you can do with the app, what you can do with Google Earth Engine. So think about in the past, right? If we're trying to do something like this, you need to maybe go to USGS, the agency, try to download the data, and then maybe set some cloud coverage, and then do some filtering, and then need to do the mosaicing, and then trying to create the data for every year. So it takes a lot of time. Now all you need to just a few seconds. You can do this very easily. So these are some of the examples. For example, this is the one I showed you earlier, right? The drawing, you can see how striking it is, the changing of the landscape. And for example, mining and coastal expansion, meandering of rivers, like anywhere you like. As you can notice here, they're using different spectral band combinations. So it might be two color or four color composite. It depends on what the feature you're interested in. You can always highlight using different band combination. For example, deforestation, bushfire, right? Also urban growth in Las Vegas. So you can see the changes of the human environment, also physical environment. Very easy to do. Just go to the app. So next, I'm going to quickly introduce like what exactly is Google Earth Engine. And so I'm sure most of you have used Google Earth, but keep in mind they're very different products. Google Earth basically is a virtual 3D globe, right? You can read the satellite imagery, you can navigate, you can turn on the 3D buildings, but you cannot do any analysis. It's just here I'm going to use an analogy here. Google is just like an image viewer on the Windows system. On the other hand, Earth Engine is just like Photoshop. You can do all kind of fancy stuff and computation. And the nice thing is that you don't need to install anything on your computer. Everything runs in the cloud. So you don't have to download data. You don't need to worry about installing anything. And it can run on any platform. So it's very, very nice. You can go to the link. And so Google Earth Engine is free for research, education, and non-profit. You're welcome to sign up using your EDU. And you can go to the sign up link in here. And so one of the common applications is like, if you see from Google Earth, right, we have a lot of satellite imagery. As you zoom in, you have a more and more detailed imagery, but you rarely see cloud in those imagery, right? So they looks all perfect cloud free, but those are actually not the true imagery. So those are actually using Google Earth Engine to do the processing and then to give you the cloud imagery. So for example, every year, right, we have Landsat every 16 days revisit frequency. So for example, for Cincinnati, every year we might get 40, 50 Landsat imagery covering the region, and there might be some cloud, some might without cloud. But at the end, if you're trying to create an annual imagery without any cloud, how can you do that? If you use Google Earth Engine, so this is what is going to look like before and after. So, and using just basically a few lines of code, you can create something like this without having to download anything. And it's very, very powerful. So as I mentioned, you can do all kinds of things, but one of the in addition to the computational power, Google Earth Engine has a huge data catalog. Right now it has 30 petabyte of data. So 1 petabyte is 1,000 terabytes. So it's more than 30,000 terabytes of data, and it's still growing. So some of the common Landsat data or Sentinel, MODIS, or weather, climate, terrain, anything you can think of, most of data set are commonly already available in the data catalog. And if your data set are not available, you can also upload data to your account, and then you can still utilize the cloud computing of Google's engine. So you can try it out. So this is the interface. Basically, once you sign up and then go to the link, and this is what it looks like. You can write the source code using JavaScript. You can display the data here, also results or any computational result using the map in here. On the left side is where you can save your script to your account. And on the right here, basically you can do all kind of plotting, or when you query the data, you will return. For example, you click your mouse, and then it's just like ArcGIS identifier. You click your mouse, and then you're going to extract the value and then return to you. So this is the interface of the JavaScript API. It also provides Python API, but they are very different. So Google Earth Engine, basically you can categorize the functionality into 2 groups. The first group is doing computation. So just doing computation, you don't need to visualize data. And the other part is doing visualization. So once you finish the computation, you want to display the result. So JavaScript API has both. So you can do computation, you can also do visualization. But Python API, most of the functionality is just doing computation. It doesn't provide you anything how to do visual data. So it's not very convenient, but as students and most of the students actually get started with Python rather than JavaScript API. So, and the reason for this is that JavaScript Python API has a lot of plotting or visualization packages, and you can also integrate with QGIS, also Jupyter Notebook. So this is basically the motivation behind why I develop these packages. And also you can integrate, for example, with deep learning and other machine learning packages. So it's very, very powerful. And so this is summarize what I'm trying to do. So the JavaScript API, you have everything. Python API, you only have this one. So here you can write source code, but it doesn't have this. So this is what the package is it's trying to accomplish, is to allow you to interactively display the data. You can do computation, but you can also display the results. So now let's dive into the package. And so it's a package for doing interactive mapping with Google's engine, and then also using IPyLeaflet, IPyWidget. So some of you might have already heard about Leaflet. So basically it's a web mapping framework that you can do interactive mapping. And so IPyLeaflet basically bring the functionality into the Jupyter Notebook environment, so they can do that within the Jupyter web interface. And also IPyWidget, basically how you design those buttons, drop down list. So everything, like you're trying to provide some interactive components on your map, so people can also interact with the map. And the package is open source, hosted on GitHub. So you're welcome to check out the link in here. It can run on Jupyter and also on Google Colab. So Google Colab is, I think I have another example in here later. I will show you later. So you can install using pip or conda, also GitHub. On the right here, I also have tutorial. As you can see on the right here, you only need use only a few lines of code. You can create an interactive map, and then you'll be able to bring in Earth engine data to do computation and analysis. And try to, if you haven't used this before, try to think about how do you do your traditional remote sensing project using ArcGIS or MV or others, right? You always need to go online to download the data and to bring in and then do data processing. So probably 70%, 80% of your time are actually spending managing the data. And you only spend a very small amount of time actually thinking about how to write the algorithm, how to do the resource design, and how to do analysis. So now basically Google Earth Engine save you tons of time that you don't have to worry about the data. You can focus more on your scientific question and how to design the algorithm to solve your issues. As I mentioned, the package can be run in 2 environments, in Google Colab and Jupyter. So for those of you who are not familiar with this, I can give you an analogy, just like Microsoft Word installed on a local computer compared to Office 365 running in the browser that you don't need to install anything in your computer. So Google Colab is just like in the web page. You just need a browser, then you can run everything. Jupyter Notebook, basically you need to install the environment on your computer and then you can run Jupyter Notebook. Although there's also Jupyter on the web, but this is like the differences. And it's very easy to get started. You can click the link here on the left side to launch the source code. Here shows you a sample script that what this one is doing. I will show you more examples later, but I highly recommend that you use the Jupyter Notebook. Google Colab is good for teaching, but the functionality is very limited because, for example, when you load the data, when you try to query the data, you usually need to click the mouse and then to based on the coordinate to extract the data. Google Colab currently cannot do that. So if you use Jupyter environment, it's fully supported. So use the one on the right is recommended. I also have a short article describing the package. You're welcome to check out the link if you are interested in learning more about this package. So for this package, I also developed a comprehensive API documentation and tutorials. You can check out the link here above. And on the left side here, you have some items. So right now, there are hundreds of functions that I developed for this package. One nice thing about this is that if you're interested in learning more, you can go to each function and then click. You will be able to see the source code behind. So basically how each function behind the scene to execute the stuff. And there are a lot of functions that you can utilize, and you can check out the documentation. I also developed a lot of tutorials for this package. And so far I have 37 tutorials, all posted on YouTube. You are welcome to check out the YouTube channel. And it's more than 9 hours. So for today, because the time, I don't have time to get into detail of everyone. But usually each tutorial is 10 to 20 minutes. So here is a full list, 18 and the other 18. So 30, I think 37 right now. So for each tutorial, I have a full-length video. So usually 15, 20 minutes. I also have a GIF animation, usually 30, 40 seconds. So if you don't have time to watch the full video, you can watch the animation to get the highlights. I also provide a notebook example, so you can reproduce exactly what I did in those tutorials. So those are all the functionality that I developed for the package, but it's only a small portion. And keep in mind, although each video is only like 15, 20 minutes, but some of those actually take me many days to actually develop. So the more important is to develop those functions and those features in those videos to be used in the tutorial. So they might take more time consuming. So it's many times of hours actually compared to the length of the video. So make sure you check out the video if you're interested in. So next, I'm going to give you something like a demonstration, like what the package is actually doing, what things you can do. So simply, if you have used Earth Engine before, you can most likely you already have some JavaScript source code. And so the package actually allows you to automatically convert the source code from JavaScript to Python. So you don't need to write any source code, just click copy and paste, and then you will want to change the language from JavaScript to Python. And then you can run this one interactively on your browser. As you can see from here, right, you copy the script from the official API documentation, and then just click the button, and then convert this one, so then you can load the data. And for example, Landsat or any data set from the data catalog. You can also search the data. So for example, you can type any keyword, for example, land cover, and then you can select from the list from a bunch of data set, and just one button click, then you'll be able to load the data. So keep it in mind, these data are not just like data layers that you just visualize. You can also do computation. So for example, land cover, right? I want to extract, they say, for example, for Ohio, what's the urban area, right? How much, what's the area of surface water? What's the area of different land cover, right? In the past, you need to download the data and then to extract one by one, but now using Earth Engine, for 3 lines of code, you can get all the computation, you can get all the statistics, and you can also export the results. So very easily, without having to download anything or to install anything. You can also search the API. Also, for example, here I imported all the API into the Jupyter Notebook, so that you don't have to like go around and search in the internet. So if you also have data from your personal account. You can also import data from your personal account directly from here. Again, for each feature here, you can go to the video, you can take a look at the animation, you can also take a look at the notebook example. I'm just trying to give you an overview, like what can you do with this package? What can you do with Earth Engine? Just to give you some idea. And if you want to learn more, then you go to the video to see the details. Also, you can bring in, for example, web services. Okay, there are tons of those web services on the internet, and you can actually bring those into the Jupyter Notebook environment. Just select, and then so that you can utilize those available web services without having to download the data by yourself. You can also create something like this, a split panel map. If you see from the source code, right, 1, 2, 3, 3 lines of code, you can create something like this very easily. This is just an example. You can create, for example, to compare land use, land cover before and after a certain event, for example, natural disaster, tornadoes, hurricanes, or something like that, anything you want to compare. Then you have 2 data layers, and then you can use the function to create something like this. So this is very common in social media or in the news outlet. You might see this one very often. And the next one is how you can use the inspector. So for example, once you load different data layers, you can activate the inspector and then click on the map. It will return you all the data values, right? So for example, in here, pixel values or the vector attribute, everything can be returned right in here. And you can also do interactive plotting. So if you see from this example here, this is a Landsat global data, right? If you're trying to see the spectral signature for different features, you just click your mouse, load the data, click your mouse, and then you will see the spectral signature. You can also do multi hyperspectral data, so like hundreds of bands. And this is where you can customize the plotting options. Again, everything is already simplified, so you don't need to write many lines of code. If you're using JavaScript, that might take you sometimes hundreds of lines of code. So the package actually simplify the process that you need to do in order to do something like this. And again, so you can use the time series inspector, right? In this case, net imagery, 1 meter resolution for the entire US, and you have multiple time periods. You can load the data for any location. You can also do that for Landsat data since 1984 for any location. So just do a rectangle, and then we do the mosaicing, cloud removal, everything, and then to create Landsat time series imagery for you for any location around the globe or for a specific county or state, depends on your location. You can also load, for example, as you are doing GIS, most likely you're going to encounter vector data like Esri script files. And so keep in mind, everything right now running in the Google Earth Engine is in the cloud. You have data in your local computer. Those cannot actually interact with each other. So you need to basically load the script file and then convert to cloud object, and then you can do cloud computing. So the function, the package also provide you a way that can quickly convert data from your locally and to the cloud, and then you can do computing with Earth Engine data catalog. Similarly, you can also do raster data. So if you have some GOT data set on your local computer, you want to load this data, two data layers together so you can compare with Earth Engine data, you can also do that as well. As you can see from here, 1 line of code, and then you can get that one to the browser. You can also publish interactive map. So in this case, that's like DM terrain. So once you visualize this kind of data layers, you want to publish to the internet. So how can you do that? Again, 1 line of code, you can publish one as an interactive app, and then you can put the link on social media or Twitter or on your website. People go to the link, click, and it will pop up, and it's still interactive. So it's not like in the traditional way that you generate the data set and then you put on your website or FTP, allow other people to download. But this is giving people the way that it's still interactive and people can visualize, people can still interact with the map, click the button, click the mouse to extract the data. So everything is very still interactive. I think this is the last one. So you can also publish this one as a web app on your local computer or using some free web services. And earlier, the web app that I show you how to create the Landsat time lapse. So that one actually is using the free web service. So if you click the link, it will take you to, so basically it's a Jupyter notebook, and then you can deploy to the web. Once it's deployed, it will execute all the source code, and then to give you something like this. So after that, then I can, for example, earlier, show you earlier, I can do it for any location, right? So if you're interested in the changes of around, let's say UC, right? Again, you can draw a rectangle anywhere and customize the parameters. And after that, just click time lapse. You can change this if you want. You can also change the band combination, and you will give you the Landsat time series for the past 37 years. Simple and easy. So save you a lot of time that you don't have to go to anywhere to download the data. Okay, so that's about the kind of some of the key features of the package, and there are a lot more features. I don't have time to get into each one, so just give you some flavor. And then if you find it useful, then you can explore the GitHub repo, look at the source code, look at the YouTube video, see if you find it useful. So next, I'm going to quickly introduce the Earth Engine QGIS plugin. So some of you, if you're doing GIS, you might be either using ArcGIS, or if you use open source, you might be using QGIS. So right now, there's 3.14. You can install on Windows or Linux or Mac computers. So once you install QGIS, you can go to the plugin, and then you can search Google Earth Engine. You can also click the link here to go to the QGIS plugin repo. Keep in mind, I don't develop this plugin, but I do develop over 300 examples. You can use Google Earth Engine with QGIS. So you can go to my GitHub repo, you can take a look. And so the next one here, I'm going to show you on like animation, a demo, how you can utilize those examples. So for example, once you download example, you just need to load the data, and then just click run, and then you get the data to QGIS. So similarly, it's just like in ArcGIS, right? You have the Python scripting. You just click open the script, and then load the data, and then execute, and then the data there will be displayed on QGIS. So it's very, very similar. But again, this is everything right now running in the cloud. So it's basically when you execute the source code, it's going to grab the data from Google Earth Engine, and then Google Earth Engine return the data layer. It's basically a web service, and then you can add the web service to QGIS. Very, very powerful if you want to utilize our Google Earth Engine. Okay, so that's about the QGIS plugin. And lastly, I'm going to introduce some applications, like what can you do for research, right? So those might be nice, like for fun, but can you really use this for doing some scientific research to address some scientific questions? Of course you can. It has the literature has been skyrocketing during the past few years on Google's engine. So there are hundreds or thousands of papers out there, but I'm just going to show you one example that I did last year. So this is a paper published in remote sensing environments. So we use Google Earth Engine to do surface water and wetland inundation dynamics. You can look at the URL here. And so quickly, I'm going to show you like what this one is trying to do. So for example, I'm interested in mapping the surface water changes. For example, in this case, the Prairie pothole wetlands. If you see from this in here, these are all high resolution area imaging, 1 meter resolution from the USDA. And every 2 to 3 years, we have national coverage for the entire US. And the data set is huge. In the past, it's not possible to actually do data processing for a large scale. But now, because of Google's engine, it has all the data already there. All you need to do is just to figure out like what you want to do with this data set. You don't have to worry about the stories or the computation. So in this case, if you look at the image on the upper left corner here, 2009, right? If you see these features, wetlands, it's a relatively dry year. Those wetlands are basically disconnected. And throughout the year, you can see, for example, in 2014, right now becomes a much wet year. And you can see those wetlands actually merge together, become basically a larger wetlands. And similarly in 2015 and 2017. So how to actually characterize or quantify the changes, right? We know that it's changing, but how much is changing and what's the speed, what's the extent? So if we can utilize this data set and then to do something like in the cloud in an automatic way, it will save us a lot of time. So here shows you a quick result how I utilize Google's engine to do the mapping. So if you see, this is just one time period, right? Here shows you 6 time periods. So if you look at just 2015, the boundary here in yellow color. So this is what is being extracted using Google's engine. So you can see pretty nicely it align very well with the boundary of those wetlands. On the right here shows you kind of water occurrence. So I have 6 time periods, right? So each location might be detected as water or non-water at a certain time. So if it's 6, that means lake pixel is being detected as water in all those 6 time periods, right? So the more likely those are permanent water. You also have some pixel values like 1, 2, 3, right, along the boundary. So those are more like temporary water. So you can see actually this gives you a nice way to demonstrate how dynamics of those surface water and wetlands. So from temporary, seasonal, and permanent, and it changes throughout the year. So this doesn't cost any data storage on your computer. Use Google's engine, you'll be able to run this one at scale. So you can actually do that for a large area using this national data set. So compare with the one that I developed with the so-called the JRC, so water extent. So this one is developed using Landsat data 30-meter resolution. So as you can see from the boundary here, right, those zigzag, those are pixelated because those wetlands are, some of those are pretty small. So the median size is less than 2,000 square meter. So less than 2,000, maybe roughly 2 Landsat pixels. So using the traditional Landsat data, you won't be able to detect those wetlands. Now using 1 meter, you can map those wetlands pretty easy. So if you see the my mouse in here, those are red arrows pointing to the location that Landsat data were not able to detect those wetlands, and also the boundary, right? Clearly the differences between this one and this one. And also on the right here shows you the national wetlands inventory. So this one was the national data set is very fine detail. It used to be manually digitized in the 1980s, and now it's very outdated. So the agency actually didn't have money, actually a budget actually to update the wetland inventory. And if you can see from here, right now it's much greater. So those wetlands are getting much bigger. And if you compare to this one that I developed, right, this is something you can quickly do using Google's engine, and then use this to update the current status of the wetlands. Very useful. You can use it not just for water. It can be any other land use, land cover types you can think of. The data is there and the computing power is there. You just need to think about, oh, what do I want to do with this data set? In the past, it's not possible because you have to download terabytes of data to a computer. Now everything is using a browser, and you just need to develop algorithm to do that. I also develop an app, so all you need to just you can click the link to go to the URL if you want to check that one out. I also provide the source code, so everything is reproducible. You can do all kind of plotting. So you just need to click your mouse on the map and then select one water set. Then it's going to get all the data, net imagery, mosaic, length together, and then do automatic mapping. So there's no human intervention. You don't need to customize parameters. Everything is automatic. So it's not perfect, but it saves you a lot of time compared to the past. It is not possible in the past. Lastly, I'm going to show you some of the application. For example, you can, earlier I showed you the application that you can develop using Python and Jupyter Notebook, but you can also develop this app using JavaScript. So if you go to the link here, upper right corner, you can take a look at some of the apps that I developed. So for example, NAIP imagery, 1 meter resolution, anywhere for the US, like nationally. And if you can see, for example, on the left side here, you can select what year you want. So for NAIP imagery, we have near infrared band, the 4-band NAIP imagery since 2009 up to right now, I think right now we have 2019 data. So if you zoom in, for example, you can check any location. Like, so this, you might have seen this one earlier in my PowerPoint slides, right? On the left side is 2009. So you can see from here, 1 meter, very detailed. On the right here, right now is 2017. So you can clearly see the changes. Again, location doesn't matter. It's nationwide, so we can do that for any location. For example, you can do that here for let's look at this one here, Cincinnati, for example. It might not have data, for example, on the right here, 2017, but it might not have data for 2009. So all we need to do is go back and take a look, maybe 2010. I'm not sure if we have data for 2010. And then from here, you can zoom in. Maybe that's the 2011. Right, so 2011 we do have data, and then 2017. So and then from here, you can take a look at, for example, at UC, right? So if there's some construction going on, you'll be able to identify. Right, you can clearly see the changes. But this is like high resolution, so the projection sometimes might have some issues, but you get the idea. So all the data set right now is in the cloud. All you need to just request, okay, I want data set for this region. And once you get the data, you can develop the algorithm to do all kind of a computation in the cloud. So there's one like app that you can take a look if you want. I also have some other apps in here, like show you how to do that. And similarly, there's another one. So if you're interested in just in a specific region, I want to get all the time series imagery for this location. All we need to do, for example, this is the by watershed. So you just click your mouse somewhere. So for example, click your mouse, and then you will go to Google's engine to search the entire data catalog for this specific watershed and mosaic in together by year. And then you want to have multiple years, like time series data for from the entire data archive. And you will be able to see that one shortly. It might take some time. So because this is the data is huge, sometimes maybe tens of gigabytes for one specific reason. So once you get the data, then you can do computation. Lastly, if you want to learn more about Earth Engine, you can also take a look at the other GitHub repo from here. Shows you 360 examples how you can do that. You can go to the repo and check a look at the table of content. You can also submit a request on my GitHub repo. You're also welcome to join the GMAP Slack channel if you want to have some live discussion. You can also leave comments on my blog or YouTube or Twitter. Okay, thank you very much for your attention. So that's all for my presentation. I'll be happy to answer any questions that you might have.
Yeah, perfect timing. I think this is perfect timing. Again, he's following this trend, and everybody's doing the YouTube these days. Mm-hmm. In academia, it's the same thing. So we're gonna learn a lot. Let's open these questions and comment from the floor. Please go ahead.
I will start.
Yeah, Dr. Lu.
Can you hear me? Yeah.
Yes.
Yeah, I always have lots of questions.
Yeah, that's a good thing. You're a good scholar, yeah.
First of all, Chu-Sheng, I want to congratulate you getting a faculty position at the University of Tennessee. Thank and you. Also getting a sizable research grant. Yeah, congratulations.
Thank you.
And I have always said that one of the key indicators of the success of our graduate program is to place our graduates in PhD granting departments. You did it. Thank you. And
it's
you
kind
made
of
us
like not a direct route, but eventually I go into
I just feel I want to say that. Enjoyed your presentation. I learned a lot, and what impressed me is obviously the ability to deal with huge data, which was not possible in the past. And also this time series of data, like you were talking about the 30-some years, even longer, which would not be possible. So I think that this is indeed a breakthrough. Now, what I'm curious about is that with this enhanced data support and the processing support, what kind of new findings in terms of the scientific research, scientific knowledge that might be generated through this kind of platform?
So one quick, like most of the application right now, because as you mentioned, in the past, the data is not like really can be managed on a local computer. So when you're trying to run those computations on a local computer, and so some of the application in the past few years, especially using Google's engine, is to do global scale. So one of the paper, early one that was published in Nature 2016, is doing global surface water mapping and doing those like for the entire Landsat data archive monthly. So you can actually do the mapping, for example, using Landsat data monthly. You can get a surface water map every month, and then you can do you can analyze the changes. Think about it, that was not possible in the past. And in that paper, it actually described that if you use the traditional way to do that, it actually took, I think, like several thousand years of trying to get the same, like the computing hour. It takes 7,000 years. And now those are just within a few days, you can get those kind of data out. And so it's basically, you can do continental scale or global scale. You can do surface water, you can do urban mapping, you can do deforestation, pretty much anything that remote sensing can deal with in the past. Right now, you can basically, you can scale up. Traditionally, if we do remote sensing, most likely we just do, for example, one county, one state, and maybe one continent. But it's very rare that you can go to like global scale and still like at a high resolution, using high resolution, like at least Landsat like 30 meters. It was not possible. If you do global scale, like 10 years ago, maybe you just use MODIS, 1 kilometer, or even coastal resolution. Now, basically, temporal resolution and spatial resolution doesn't matter. All we need to think about is how do I design my resource to answer the question, and then let Google handle the computation, especially if you're doing time series. It doesn't matter like 30 years or 40 years. The algorithm is still the same. You don't need to change anything. You just need to figure out what's the area I want and what you want to do. And the more important is the algorithm and your design. It doesn't matter like I want to do it for, if your methodology is good enough, it can be generalized just for Cincinnati, or it can be for the Ohio State. You can do it for the entire US. You can do it globally. So that's one thing that's very, very transformative, is that you focus more on the science, less on the data management. Like I need to download data, I need to manage the data. And it has a huge data catalog. Pretty much anything that we use traditionally is already there. And you also have a bunch of data products. I can show you here, if you go to the Earth engine, the data set, it's huge. For example, this is just say Landsat, for example, all the entire data archive, and this is just Landsat 8. You also have, besides the traditional original data, raw imagery, you can have already all kind of atmospheric corrected data. Everything is already there. So we used to have to use Envy to do correction, all kind of stuff. Now, those things already be done. And you also have tons of those that derived products, for example, NDVI, right? And then when you click in, you all you need to do is to figure out like what's the unique ID. So every data set in data archive has a unique ID. Basically, you can think about a person. And right now, in the past, we have to figure out like how to do everything by ourselves. Now, basically, you need to think about like, as long as I know who that person is and that person can do something, I just ask that person to do it for me. And I just need to coordinate the efforts. So this is changed from like doing everything from by ourselves to doing management and doing the design. So it's a more like higher level management. I think that's something that's very transformative.
My second and the final question is, I mean, obviously this is for image, remote sensing image. Do you envision a similar product available for vector-based socioeconomic data?
Yes, actually it already has. So Google is very powerful for raster processing. It also has some relatively limited vector data processing. So the idea here, why it's better for raster, not for vector. So think about here how Google Earth Engine is doing the computation. So it's like this way. When you are doing the loading the data, so basically Google Earth Engine has thousands, tens of thousands of computers. So when you're doing the computation, it's basically subdivide your image into smaller tiles. So it is send this one to one computer, do the computation, and then return the result. So it's just piece by piece. If you're doing vector, think about it, it's a bit more difficult to actually subdivide. So raster, you can also row and column, easy to subdivide, but vector is a lot more difficult. So it's a bit difficult to scale up. So it can do some relatively like simple operation, but when you are dealing with a polygon with like tens of millions of vertices, it's not very computational efficient. So there's some of the bottlenecks. And the other one is not very good, for example, for doing, let's say, hydrological modeling. Anything that if something is related to something else at a distant pixel, it doesn't scale up because it's difficult to subdivide the type. So if it's only like small neighborhood, it's okay. But for example, if you say trying to delineate this stream network, this pixel might be related to a distant like outlet pixel, and that one is not computational efficient right now in Google's engine. But it might have some improvement in the future. But right now, this is the best thing that you can do with Earth Engine is doing time series just based on the location, does not rely on the neighborhood. And so you can, based on the time series, you can have one pixel. You can do hundreds of years. It doesn't matter how many you have. And it's very efficient. That's one line of code. You can do that for all the images. So for example, they say you have time series for the 37 years, right? Those operations are all the same. As long as you know how to do operation for 1 year, and then you just use a map function, basically a looping, and then you can loop all the images. So, and it's very efficient. So that's the base kind of application that you can do with Earth Engine.
Thank you.
Mm-hmm.
So let me re-summarize question and answer. So Dr. Lu asked you, the Google Earth and then Earth Engine is pretty much the efficient regarding those raster data and the physical environmental data. He was asking two questions. In a modeling, data modeling perspective, you're right that the raster base, they have a better efficient for the plot tree and any kind of an algorithm to make this fast to zoom in out and zoom in, and that has been available more than 20 years ago when I was a graduate student. Anyway, vector data do not have those kind of efficient algorithm to make the engine base. But the other issue is, like for example, he asked that do you have any socio-economic like the census data that this Google has this kind of.
You see my screen here. So this is where the census data, you have pretty much all the census data, census block, census tract, and also state, county, those are all available in here.
Here, so we don't need to go to census.gov anymore?
You still can. It's not like all the information, but those are some of the basic ones you can get from here. For example, if you're interested in transportation, you need to have like a roads network for the entire US. It's up here.
Yeah.
Yeah, and as you can see from here, how many lines of code? 4 lines of code, you can get the data. And then you can do all kind of extraction. For example, I just want the road network for Cincinnati.
So give us the mechanism and behind those things. So the Google has their server to make this possible to in their server to instead of we going into the census.
Yes.
And then,
so basically,
right?
So they have the data set. The data set come from actually from Census Bureau. So the data actually from those agencies, but they put those data and then put it one in the cloud server and made in a format that is, you can do parallel computing. It's not like traditional, just like save the data on our local computer. No, it has tens of thousands of a computer. And so when you do the computation, every computer is doing a small piece. So there's a kind of some engineering like setup how to actually distribute those data. But if you, for example, for this US census rows, if you download this one, this is probably tens of gigabytes of data for the entire US. It's very, very detailed. So it takes time to actually, you can also upload data to the cloud if you want. So if you click this one, for example, I can open in the code editor. And so as you can see here, it takes you to the code editor. Now, if you see from this one, I just need to hit run. And then, so basically this is the ID, what's the name of the data set. And now how will I want to visualize this data set? And then I want to set the location, the center, add this one to the data layer. And now you see, you have the data set for the entire US. And you can zoom in, you can zoom out and see how detailed it is. You don't have to download anywhere, right? So the computation is like on the fly. You only compute based on your zoom level and based on the location. So it's not basically dealing with the data at its native resolution. For example, if you're doing with Landsat data, 30 meter, when it's doing the computing, it depends on zoom level. It's just, if you just get the overview, this might, you can compute using 1 kilometer, 10 kilometer. You don't have to actually compute at 30 meter resolution. So the same idea is like this. And you can load the data and you can pretty nicely to like anywhere. So this is give you a quick way. You can also export the data if you want. It doesn't just live in the cloud. You can export the data to your local computer to do photo processing if needed.
Yeah. Oh, one more question before we actually closing up, wrap it up. Can anybody? Please, graduate students.
Hey, I want to talk, okay?
Okay.
Hi, Kunsen.
Hey.
So I think that you convince us that this is extremely powerful tool. And obviously it is beyond anything which we know. It's kind of like, you know, the artificial intelligence comparing to the normal person intelligence. Yeah?
Yes, you can say
but as you well know, the society, including the science, evolved in the mysterious ways. So when about 15 years ago, I was developing the automatic mapping of geomorphic mapping of Mars. And I wanted to sell the geomorphologists on that. And they told me, we are not interested because when somebody is doing this manually, he or she thinks and became familiar with the issue. If it is done automatically, people don't think. And as a result, we have hundreds, if not thousands, papers about nothing. So what would you say that maybe this fantastic tool actually going to make a research worse than a better? I understand that it could be much better, but the question is there a danger that it just became too easy?
Yes, that's kind of two A's question. So basically it can just think about, I think the similar way, like for example in ArcGIS, right? In the past, we use ArcInfo workstation. Everyone need to do the coding from the very beginning and then to write source code. Now ArcGIS or ArcGIS online, it makes everything easier. Just click the button. All the students actually right now can do those things. But behind the scene, they don't really have a good understanding of what's behind the mechanism, how actually, when you click the button, which actually what it's doing. So Google certainly makes things easier. And we can utilize the computational power, but also there's something that right now there's a trend. When, for example, as instructor, when we teach students, we actually need to also talk about the theory behind all the research, how the everyone is executing. We don't want the students just to go and click and copy and paste without thinking. That's not what we are supposed to train the next generation resources. So I think it's very important. But for me, because I do all the coding right now, for example, the package, I try to provide you just one line of code. You can do a lot of things. But if you don't look at my source code, you didn't know what I did. So that's why I introduced. If you want to contribute, you want to learn more, you need to go to the function and then look at the source code, and then so you have a much better idea. For me, I certainly like know a little bit more because I build those packages from ground up. So I learn a little bit. But the things that I always want the student to know is that things are easy, but you need to think a little bit more behind the scene, not just clicking the buttons. Otherwise, we are become more and more stupid in the future. So this just my.
We have fantastic data. The problem is what we can do with this. There are some people who definitively know what to do with that, but you know, people to tend to. It will be very easy for somebody to calculate something and just send for publication.
Yes,
because it doesn't need a few months of work.
So basically, I think it's a good thing actually for us. So for example, if we supervise students, now, for example, for you, you don't have to know like how to do the coding in Google's engine. You just think about the idea, and then the student, they can learn it by themselves, and you don't have to worry about the location or the data set. Everything is already there. You just need to think about the resource design. and then that the students or your advisors actually to think about how to implement. So when they're implementing, they will have some issues, and then they will gradually learn how to solve the issues. At the end, they will still know how to think. But you don't want to provide, you do the coding and then just provide a script to them, and then just they open and then just click one, okay, done. That's not what we want to achieve. So it's very different.
Very good. I think one 4:57. So I think we have 2 or 3 minutes. Last question from the graduate student. Otherwise, we will wrap.
I got a question. So we have learned how to visualize and also
why don't you introduce yourself? Who is it?
Yeah, could you guys see my? Yeah, I'm Shane, a new graduate student from at the university. I joined the PhD program this spring semester, so this is my second semester. So thank you, Dr. Wu, for the presentation. So we have learned how to visualize and analysis, also download raster and vector data. But is there any ways for me to use Google Earth Engine to like visualize or download the street view data? That's my question.
No, there's no Earth Engine. It is so for Street View, you need to use the Google maybe the Street View Google Maps API. So this is totally different. This is just basically for satellite and area imagery processing. It's not for like Street View imagery. So, but it might have something in the future. But this is not right now incorporated in the data catalog of Earth Engine.
Okay, I see.
Mm-hmm.
Thank you.
Okay.
Yeah. Hi, I'm sorry.
Yeah, go ahead.
Okay, my name is Esteban. I'm also PhD student from UC. Let me ask, thank you very much for your presentation.
You're welcome.
I wonder if, what is the next, from your personal opinion, what is the next endeavor in this Earth observation science? I mean, it's clear that we have developed a lot of remote sensing techniques,
Mm-hmm.
new data sets, higher resolutions for any kind of data set. But what do you think that will be the next step? It will be related to how, I don't know, how conciliate field measures with observational measures, or could it be more theoretical advances? I don't know. What do you think about it?
From my personal observation, I think remote sensing basically is improving over time. Basically, when we do remote sensing, we need to deal with a scale. So you basically spatial resolution, temporal resolution, spectral resolution, right? So those things can all change. And as I mentioned earlier, like 1 meter resolution for the US, you only have that for every 2 to 3 years. But in the future, right now we already have, like, for example, planning imagery. You can have 5 meter resolution pretty much daily or weekly. So the data volume is actually skyrocketing. And traditional way how we handle those data sets is basically not very efficient. Now with Earth Engine, we can actually handle those data sets. So the more important, I think, right now is for those engineers, how to develop like better instrument and how to get better data. And for us, it's like a researcher, we need to think about what kind of questions that are still out here that is not being addressed in the past because of the data limitation or whatever. Now, we don't need to worry about the computation. So basically, the computer science or the engineers, like Google, those big companies, they can think about how to do that more efficiently. For us, I think we need to think about more on the science and also how to best utilize those satellite data or aerial imagery to address those questions that are more like global scale. For example, right now, because of the pandemic or whatever, everything right now seems to be like a large scale. So using this kind of platform, we can actually address some of those questions that we are not able to do in the past. So certainly there are some kind of ways that you can think about this, but I think it's getting better in terms of computation, also in terms of data quality, and also in terms of data volume. But there are still a lot more work need to be done, I think, in remote sensing. I don't know if it answer your question.
Yeah, no, it sounds great. Yeah, what I would like to hear is that yeah, we are like moving from regionalism to more globalization, I mean, to global scale.
Yes.
So it, to me,
Okay.
yeah. For the other one, I guess that it's correct to say yes. The computer science will keep improving the methods, but we will soon arrive like the GPS. I mean, more resolution that is, I guess, not needed. But but who knows? Thank you very much. Great presentation.
Thank you.
Yeah. Thanks for Dr. I think let's wrap it up. Here's a take home. The lessons from today's lecture. What Dr. Wu was trying to convince is, we used to use a lot of time to download the data to the computation, and we are less have time to produce our scientific question and answers for the research. Now, take home lessons from today's lectures is not beyond these details. What he actually showing the technical things is like what we have to use the US Census and USGS.gov. He said that let's utilize Google to make your research production or productivities higher, increase. That's I think we should take the lesson from today's lecture beyond those the technical side. Okay, Dr. Really appreciate those who are interested in, and for the master want to go to University of Tennessee for the joining the PhD. You agree to contact him, and if you have any questions, driving by 3, and he's more than happy to give you a copy of the Chinese software. And he's our alumni. His heart is in University of Cincinnati, and Dr. Lin Nu brought him from the Sandhurst University. He's our first, one of the first the generation. So we department is very proud of his product. We keep wishing him for the best and his career success. Let's hope for the best. Thank you, everybody. Let's wrap it up. Bye bye.
Bye.